Good morning, all. So I think it's time to start today's class. So as I was mentioning, we have already finished the PLC understanding part. The basic instructions which are required uh, for this course is already being given to you. Now we will be moving towards the next section of the numerical control. And I'm sure that you have already started the lab component of this. But we'll discuss the internal details of the numerical control in our one word. So let's start today's class on the numerical control. As you all understand, when we talk about the numerical control, is a type of a programmable automation. So various type of automation we have understood: fixed, flexible, programmable. So when we talk about the numerical control, it is basically with the help of a instructions you will be able to execute the sequence of you will be able to control the sequence of operation of a machine tool. So in this case, the mechanical action of the machine tool is controlled by the program, as you already seen, and this is a part program. We normally call it a part program because it's more related with the CNC machining, so we call it a part program for the same. And as we all understand, the part program is basically a kind of an alphanumerical instructions. So you have some alphabets being used, and then there are certain numerical values you are specifying for different parameters. So in this case, we'll see that the numerical control is the way in which you will be controlling the motions and the logical control of a machine tool or maybe a non-machine tool applications. So the application categories, if you see for the numerical control, most of the time when we talk about numerical control, only the CNC machine comes to our mind. So that is why I will be emphasizing on that numerical control is not limited to the CNC machines only. It has a non-machine tool applications also. So machine tool applications are already known to you. So drilling, milling, turning, combination of these operations as well. So these are the primary applications of the machine tool. Non-machine tool application, we are still looking forward to control the motions and the operations of a system. They are assembly systems with the help of a robots. There's an inspection systems like CMM, and there are even the 3D printing applications, which is again we call it may not be coming in the standard machine tools which are doing the subtractive operations. So these are some of the non-machine tool applications. And whenever you look at the operations, how we look at the machine tool, there is a cutting head, or there is a deposition head, or there is a measuring head. So we call it a work head actually. Whatever you will be using, whether it's in a cutting tool or as a probe, or it will be in a extruder in a 3D printing machine. So anything which is act as a work head here. So we will be trying to control the relative motion of the work head with respect to the workpiece or the work part. So there are relative motion between the work part and the work head. Work head will be carrying a cutting tool. It can be carrying a probe for the measurement in the CMM, or it can be a deposition head over a surface actually. So the surface, if it is in a machining operation, you will already have a raw material, raw part. If it is a deposition process, you will be having a bed actually, so on which you will be doing layer by layer depositions. So that way, the idea of the numerical control is that with the help of this alphanumeric data or the alphanumeric code, we'll try to control the relative motion of the work head with respect to the work part actually. Fundamental elements of the NC technology or NC system we need to understand. We were discussing earlier also in terms of the software programs, but let's see that when we talk about the basic component of any NC system, whether it's in a non-machining or machining type, you have the part program or the program that you would like to execute here. So that is the instructions that you want to give it to the machine for the relative motion. Then you have a machine control unit, which is basically controlling the different motions of the logical controls of a machine tool. So machine control unit is kind of a computing environment or computing system. It's a hardware with the mix of certain softwares. It also acts as an operator interface also to the machine. So MCU has different features that we'll discuss. And finally, you will be having a processing equipment. It's in a mechanical system or the electromechanical system, which will be performing these operations. So if you look at the part program, you have these kind of instructions you might have understood by now only, or earlier also you might have done some course on the NC, you will understand these instructions. We will go in detail on these instructions as well, but idea is that you have some alphabets and then there are some numerical values which machine need to understand. So then the machine control unit, if you look at this, this is again, as I was mentioning, it's a hardware, control hardware that stores the program. And see, now when we talk about the terminology of the NC and CNC and the DNC, we need to understand numerical control is just meant that with the help of a numbers, you would like to control the motion part over here. But when we talk about storing the program, selecting the program, editing the program, all these functionality will come with the CNC when we say computer numerical control. So today we are using this terminology interchangeably, but mostly we will be addressing the CNC part actually. So we are assuming that there's a computing system over here which will be doing all these functionalities, which will store the program and execute by converting each command into the mechanical action. So idea is that machine will pick up any of the instructions over here. For example, this instruction, then it has to just execute this instruction. So when we say the execution means for a machine tool, execution means there's a relative motion to be generated between the work head and the work part that need to be done. And finally, the machine or the processing equipment decides what exactly will be the operation. So the CNC will still be giving this command X 100 X minus 1.5. So this may be performing a cutting, this may be performing a deposition, this may be performing a motion of a measurement probe. So this program doesn't define that, only the preparatory instructions at the top will be defining some of those instructions, but it's all how the machine tool is being designed basically to move the work head on the work part. So if it is a cutter, then it will be doing subtractive machining. If it is an extruder, then it will be doing the deposition. So these are some of the very basic things. Already, I am sure that some of you may be aware of these basic understanding also, but I'm just giving you a quick revision on that part. Whenever we write the part programs, they always be written with reference to certain access systems. So we need to understand those access systems, because when we interpret the part program or the machine will interpret the part program, they should be in the same convention actually. So if I am saying that the plus x is in this direction, then my whole part program will be written assuming that the plus x will be in this direction. And same is true with the machine also. So machine will also execute the plus x motion in the same direction which we are writing the part program. So in this case, you'll see that this is your positive x-axis, this is your positive y-axis, and this is your positive z-axis. So we should always be very careful about the positive z-axis actually, because that is the most I should say the detrimental part if you are not considering the plus z and minus z, because your tool head may plunge into the workpiece if that is not being accounted for properly. Rest are also important, but the most critical is the z, because immediately the minor error in the plus and minus will make the tool head goes inside the workpiece. So we should be careful on that. So plus z above and plus y inside the machine and the plus x on the right hand side. So once you understand this, then the opposite axes are the minus x and minus y and minus z. And rotation about these axes, rotation about these individual axes, we will be naming them in a plus A, plus B, and plus C. Right? So that is what we need to. So if you see here, the work table and work part, that is where you are placing the job or the work part that you want to process, will be moving with respect to this axis system. This is for the flat and prismatic components, and when it comes to the rotational parts, so this is applicable for all machines where you have a Cartesian coordinate system, and then you will be moving the linear motion and the rotation motion of the different axes. But when it comes to the rotational parts similar to the lathe machine, then you will be having axis system in this way that your plus. So this has been drawn vertically, otherwise this will be the horizontal one. This is not in this format, it has to be in a horizontal. So plus z will be outward and then minus z inside, and then and according the plus x and minus x. So plus x and minus x will be important when you will be using the turret or the tool carriage basically in the lathe machine on which side actually. So it's on other side of the machine or it's towards the operator side. So that we'll see when we discuss the lathe machine. But this is the current convention we need to understand, because once you start writing the part program, I think that will be used for this. Now, when it comes to the motion control systems, because we will be spending a little bit more time on understanding the motion control system. These are the two important motion control systems we always have in the machines, depending on the type of machine. For example, if you're talking about the drilling machine, what type of positioning system you will use? Anyone?
That point to point.
Point to point, yeah. So because our intent is to just reach out to a particular coordinate, and there you have to do the operation, and it doesn't matter how you reach to the next point, it only that particular coordinate matters. So that is how the point to point positioning system will be used, whether it's in a punching operation, whether it's in a drilling operation, or this kind of operations, you will be using point to point positioning. Now, when it comes to the continuous path contouring, it's basically when you are talking about a profile to be generated or profile to be cut based on this. So then every coordinate of the cutter path is important in the case of a continuous path contouring. Right? So in this case, the most important part is that the controller which will be performing these operations are different, and they are of a different order of complexity in that case. Right? We'll discuss those aspects also, because point to point is a much simpler operation to implement, and the hardware that is being employed for implementing point to point and the continuous path will be different. As I was mentioning, there are different type of interpolations being involved in the continuous path contouring motions. So we'll discuss interpolation also, which is very important concept when we talk about the cutter path to be generated, and when we will be moving multiple axes simultaneously, what exactly the interpolation means. So in that case, the different geometries are being created with the help of the interpolation methods. So you normally see that when we talk about the part program, we only give the start coordinate or the end coordinate or certain parameters actually. Now, based on that input, the intermediate points to be generated by the machine controller. Because we are not specifying all those points. For example, if I have to do a linear motion from point A to point B, we will only be specifying the 2 points. Now, how the machine will make the motion happen between point A to B is being computed by the controller, and the machine controller will be then calculating all those intermediate points based on the type of interpolation you look forward. So that is how the interpolation means just a calculation of the all intermediate points along a trajectory that you want the cutter path should move. So that is what the interpolation means. And then we have different type of interpolations in the CNC machines. And now when it comes to the curves, basically it is always being done based on the approximations basically, because your cutter path, whatever the controller is generating, is between 2 points, point to point. So it's always in a straight line rectilinear motions that are being generated, and then these rectilinear motions will be then approximating that particular curve. So there are different type of approximations that are being shown over here. So if you can see that the inside tolerance, the outside tolerance, and then there is a both side tolerances, so that how you will be performing those approximations. So these curves will be showing you the different type of errors. So this again depend on how much is the smallest point to point length that your controller will be able to control. So all these things will be deciding the outcome in terms of the dimensional accuracy as well as the finish on the component, and that's how the computing environment that will be doing all these calculations is very important in case of a CNC machine tool. So we'll be trying to understand a little bit of those concepts as well. When it comes to the different type of interpolation, these are the different interpolations that are being available. So simple interpolations are always be there in all type of machines. So you'll find that the linear interpolation, circular interpolations are common in all type of machines. Just a minute, something happened that it's not, slide is not changing. Let me just correct that. Are you able to see the slide changing on the screen? No?
No, sir.
No, sir.
Just a minute, let me stop there. Yeah, I think it is now visible. Yes. So there are two interpolation methods which are very common in all type of machine, the linear interpolation, circular interpolation. Most of the geometries that are being generated are using these two interpolation methods. We'll discuss little bit more technical on the interpolation when we discuss the motion control part. So let us wait till then, but let's try to understand the basic type of interpolation. So in this case, the most basic method is the linear interpolation. It's a two-axis interpolation. You have to specify the start point and the end point. It will be just generating all the intermediate points from one point to another along a straight line. That is what the linear interpolation is. When we talk about the circular interpolation, you all understand that it's basically generating a circular arc, and then you need to specify the start point, the end point. Either you will be using in a center or the radius of the cutter and the direction of the cutter. So you have to specify the minimum parameters to trace out that circular path. So that is what the circular interpolation is. Now combination of these two, the linear and the circular, will be able to produce the helical interpolation. So it means that we will be interpolating circular along the two axes, and then perpendicular axis you will be doing the linear interpolation. So that's how. So this is the circular interpolation that you will do in XY plane. And along Z, if you will be doing the linear interpolation, so then this curve will be coming like this. So that is what is known as the helical interpolation. So some of the controllers are capable of doing this helical interpolation. Not all have that capability. And certainly when you go for the parabolic and cubic interpolations, then certainly there are higher order equations involved and it requires more computation power. So this is again not so common feature in all the CNC machines. So if you are looking forward for this kind of interpolation, you need to check the kind of controller will be there in the machine. And then if you are in a position to decide what type of controller the machine should have, then you can go through those specifications and understand whether it will support these kind of interpolations or not. So I will tell you some of the controller specifications, so then when you visit their websites or the manufacturer catalog, you will be able to see all those parameters which are important over here. Then when we write the part program, these are the positioning that we will be using, either the absolute or the incremental positioning. And I'm sure this also you might have done that with the G code, you will be deciding which positioning system should be used. And when it's basically referred to when all the coordinates being referred to the one common origin, then it is basically the absolute positioning system, which is useful most of the time. Because we will be addressing all the points with respect to the origin, and we can easily find out those coordinates. But sometimes it is always good to use an incremental. So next position, whatever we will be specifying in the path, will be based on the incremental position from the previous position. So whatever increment you want to make in X and Y or Z from the previous position is basically the incremental position. So you will be only specifying those values over here. So in this case, absolute versus incremental positioning. So can you tell what should be the, so let me just put the name to these points so that it will be understood. So this is A, this is B, and this is C. So what is the absolute positioning for the point B? Who will tell me?
40, 20.
Yeah, so X will be 40 and Y will be 20. So good. So you can easily find out from the basic understanding of the coordinate system. And same C is already known, it's a 40, 50. Now, when it comes to the incremental positioning from A to B, so if I have to move to point B, what should be the incremental motion that I require from A to B?
20,0.
Yeah, so you have to 20. So you have to move in x-axis 20 and then 0 in the y-axis because it's parallel to the x-axis. And same you can find out for the point C. From B to C, how much will be the incremental motion?
0,30.
Yeah, 0,30. So good, I think so you know these basic understanding, and if this is clear, then you can easily use that in a part program. Now let's come to the computer numerical control. So numerical control, as I was specifying, it goes back into the history of the development of these kind of systems. So people are using these numbers and the alphabets to control the machine. That is how they call it a numerical control. So initial numerical control system is not computing based. So they are using some embedded controller hardware, but it is not full-fledged computer that is being used with the machine. So when we talk about the CNC, we are talking about the NC system, where we will be using a microcomputer. So again, the terminology is still an old one, because nowadays we don't give much weightage to whether computer is used with the machine. We assume that it is there. So that is how it is more common to use the CNC today. But earlier, when people want to make a distinction that they are adding in a computer to a machine, and that's how the terminology CNC comes into picture. But then there are a lot of advantage that you may realize now, that because you have not seen the NC system, you are directly working on the CNCs. So you take them as a granted. These advantages are coming as a part of the integration of the microcomputer with the machine tool. So in that case, if you see, whenever you have a computer, you have all these advantages associated with the NC control, that you can store more than one part program. So when people are saying storage of more than one part program, as a computer, we already understand you can save multiple NC part program files into the computer itself, because it has a hard disk and you can save them. But when it was in a numerical control only, then you were loading the program one by one. Actually, at any point of time, you can only have one program going inside the machine, and then it will be executing. And once that completes, then you have to input the next program completely again. And that's the reason that people were using magnetic tapes and the punch cards basically to do all those activities. But now, because we have enough space into the computer, you can easily save multiple programs. You can call the programs and then you can execute them. So that's how the storage is easier when you have computers. You have options to write the program on the machine controller itself. So various forms of the program input is possible. Program editing is there on the machine tool. The most important part is this one, which is very important, that you will be able to do the fixed cycles and the programming subroutines actually. Now, many times when we do the machining operations, you may not be writing detailed instruction of that material removal. And there are fixed cycle operations that also we will discuss. So you have to just specify all the parameters in one single instruction. For example, if you are interested in doing the pocket milling, or if it is in a pack drilling operations, so in that case, you need not to write all those incremental steps to remove all the layers of the material from the pocket. So there are the cycle codes, there are fixed cycles. If you just write all those parameters in one single line of instructions, the CNC controller will take care of all those computation which require to remove the material. See, the material removal happened and it requires all the motions to be performed. You can't skip that because machine controller has to do that task for you. One option is that you will be doing all the task and writing everything into the program. Then it will be a much larger or much longer program that you will end up in writing for a small pocket milling also. So to simplify that task, this has been now programmed or given to the computers, which will do the intermediate calculations for you. So this fixed cycle and the programming subroutines is possible only when you have a computer associated with the machine tool. And they are able to do the complex interpolations also, because computers are now good at doing all those computations. So then the higher order interpolations may also be implemented over here. Then the advantage of a computer is that all the compensation calculations, the cutter length and size compensations, can be calculated by the CNC. So because now you have a computing power into the machine, it can, apart from the motion control, it will also be doing mathematical computation for you. So that is the way that it can do certain calculations, and then based on those inputs, it can find out what compensation is required for the cutter length and size. Similarly, it will do all acceleration and acceleration calculations because for all motion control moving from one point to another point, these calculations are required along all the path that is to be executed. Then advantage of having a computer is that, and today's computer, because they come inbuilt with the communication interfaces, as you may see that there is a LAN or there is a Wi-Fi or there is a Bluetooth. So you have multiple ways of communicating with the machine tool. And most prominent is the Ethernet, and it's a very important part when we talk about the smart manufacturing. The machine should be having a communication enabled feature actually. Then you will get a lot of parameters which you might not have realized that how the machine health will be monitored. That certainly I will discuss when we discuss on the smart manufacturing, because we are doing one project where we are interfacing with the CNC milling machine in the workshop and then try to bring out all the data into the lab to understand, because this machine controller will keep on giving you large amount of the data, so that you can understand the behavior of the machine, you can understand the health of the machine, the operations, basically whether whatever the precision you have defined, whether the machine is executing those precisions or not. So there's a lot of advantage of having a communication interface inbuilt into these kind of a machine tools, because then you will be exchanging a lot of information two-way between the machine tool. And certainly the diagnostics can be done. So based, once you are getting all sort of data, and then some of the diagnostic features are there on the machine itself. So you will be running some program which will be analyzing this data on a continuous basis and then find out if there's any fault into the machine, or there's a cutter wear out much faster. So all these kind of diagnostic can be done on the machine itself. So there are a lot of advantage of adding in a computer, and that is how we will be utilizing all those features with the machine tool today, that because they are already coming with the computer embedded as a part of the machine tool itself. So these are the CNC controllers. I will strongly recommend that you will find some time and then search on the website of the machine tool manufacturer, or these controller manufacturers basically. You will get to know about the different controllers, different manufacturers of the controller. I'm sure that you might have heard about some basic controllers which are available in the market. But other than that also you can now explore and understand, because now as a engineer or the MTech, you should understand what are the key features of these controllers. If someone asks you to recommend them a controller for a particular machine tool, you should understand what are possibilities on those controllers. So if you see that, if you just go into the detail, let me just zoom it out. You will see that these kind of information might be there. So up to 11 axes, 4 spindle axes, and 2 paths. So the controller has been designed much beyond the basic machining operations. So if you see that the application they are saying is the milling, turning, grinding, punching, gear cutting. So same controller will be able to meet the different requirements over here. And then you can just see this is important part which we will discuss, the 4 axis simultaneous and 3+2 axis machining. Because when we talk about the multiple axis being controlled, or they are basically performing some coordinated motion at the same time, that decides the complexity of the controller. And that is how the interpolation is very important when it has to be done for the multiple axes at the same time. So this feature is important, though it is saying 11 axes over here, but then if you see the simultaneous operation is among the 4 axes only, and 3+2 axes for the machining. So 5 axes for the machining, and 4 axes you can operate simultaneously for other functionalities. So this is the certain important part of the, I'm not going into all the features, but I will strongly recommend please go through the manufacturer's website, and then you understand what all capabilities the controllers are having. And these capabilities are coming because they have the computer inbuilt into the machine tool now. So if you see that the basic models for the multiple control applications, you'll find here. Then high performance CNC for the complex machine tools. Now you will realize that now there are additional features over here. Here you can see that it is saying up to 40 axes of the control that you can have. You can have 8 spindle axes. This is now capable of doing the 5 axis machining. It means that you will be able to do interpolation in all the 5 axes at the same time. So whenever we are saying 5 axis machining, that it means that computer or the controller of a machine can do control of motion in all the 5 axes at the same time. Now these 5 axes will be a combination of the linear and the rotational axis. I'm just looking at if you can just look somewhere, there might be the interpolation details will also be given. So this slide might not have captured, but then once because you will easily get the technical specification sheet of this controller, and from there you'll get to know about that what sort of interpolations are being supported. So that is an important part, and it's an important exercise to be done. So I will strongly recommend that all of you should please have a look at these specifications. Yes.
So what is meant by this 10 paths, sir?
Which one?
First feature, sir, to 40 axis, 8 spindle axis, and 10 paths. What is 10 paths, sir?
Yeah, I'm not also very sure what exactly this 10 path means. I need to check it. Maybe they are storing the path for the repetitive motions. So probably I will be just guessing on that, but need to be checked. So you can also check. I will also try to find it out. Okay.
Okay.
Sir,
Yes. Yes.
so in these CNC controllers used nowadays, so nobody types the GNM codes themselves. So everyone is using CAM to input the GNM codes automatically.
Correct, correct. So only they are doing minor editing on the console. Rest of the part program being generated by the CAM softwares only, because the most of the parts that are being produced by the CNC machines are the complex parts only, and writing a manual part program is not so easy for those kind of parts. So we are directly importing the part program into the CNC controller and then executing that. And this part program preparation will be done by the CAM softwares. Only thing is that we need to understand the basic syntax of the part program, because sometimes we need to validate or verify the program. But for that also the NC simulation tools are available. But if you have to do some minor editing on the machine, so if you are familiar with those instructions, you can do those edits.
Okay, sir.
Okay. Those were the earlier days where people were punching the program directly onto the machine, but it is not required. But machine has all that capability. You can write a new program and write but those are only limited to the very basic instructions. Only you can write the part program for a very small motions, which are a combination of a linear and circular path only. Whenever it comes to the 3D interpolations and 3D geometries actually, and all that programs are being generated by the CAM softwares.
So these controllers are very different from each other for every organization. Like Siemens has a numeric controller, so it is
Yeah,
different
numeric
from.
is there, Fanuc is there. So see if you see the difference in the controllers are not, the language is almost same. The part programming syntax is because they are defined by the international standards, so everybody has to follow those instructions. Only difference you will find, there are the more and more these cycles are there actually. So if you see, they are trying to combine multiple functions into the groups actually. So these are the additional capabilities. So certainly the linear and circular interpolation commands will be same in all the type of controllers. But if I have to do in a pocket milling actually, for example, so there may be the additional codes that are being used in those particular controllers. Some of the controllers will be able to take care of a specific requirement of a machining process. For example, there are certain controllers designed for the milling functionalities. So whatever the compensation required, whatever the geometries to be created for the milling, they are being specially designed for those kind of applications. So these are the variations you'll find come across the different manufacturers. So they are trying to add more value to their controller by providing additional functionalities. The basic part programming, NC control, and the access control will always be same in all the controllers.
Okay, sir.
Okay. And these days, as I was saying, these controllers also coming with an interface through which you can download the program, download the parameters actually. That is what we are trying to establish, that to a CNC milling machine that we are trying to control is the Siemens controller. It's an 828D controller. Now you can interact with the machine with the same console environment over here, which is there onto the machine. But if you have to implement any of the smart manufacturing technologies, for example, if I have to predict the quality of the component coming out of the machine, now these controllers will require little intelligence to be implemented. And this intelligence always reside outside these controllers, because these controllers are right now not implementing those kind of functionalities. Again, it's not that they don't have a capability. To a certain extent they have a capability, but then the manufacturers are not providing those capabilities. So what we need to do, we need to do all that sort of intelligent processing outside these controllers on a different computing environment, and then communicate back to the controller. And so this kind of a two-way data exchange to these controllers are very important. So there are certain standards that we need to check with the controller whether they are supporting that kind of communication or not. And currently what we are using is an OPC UA communication through which you will be exchanging the data with the machine controllers. So these are the additional functionalities that you will get, and some of the good manufacturers like Mazak and other, those who are making these CNC machines, they are trying to put all these features as a part of their controller itself. So there's a variety that you'll come to know once you do a quick survey of these controllers and their capabilities. Okay. So basic internal details of the machine control unit is almost like a computing hardware. So again, not going too much into the detail, but most important part we need to understand are now three different type of hardware requirements inside the machine control unit. One is certainly to store the program, retrieve the program, edit the program. It's a kind of an operator interfacing part. The second part is the motion control part, which will be responsible for executing or generating the instructions for the hardware, which will be making the mechanical motion possible. And third part is the logical execution part, the sequence control part. So you will see that the basic hardware will be the same. Earlier, this used to be a different hardware. So people will be having a different computer operator console, and then the motion controller hardware will be different, and the PLC will be different actually. So that's a way these days controllers are combining everything together into one integrated hardware. So, but if you see, it's a basic computing environment. So you need to have a memory onto the controller. We need to have a CPU onto the controller, and there are certain input-output interfaces being possible. And then these are the motion control parts. So you have a position control system implemented. You have a speed control system implemented. This is related to the motion control. And then you have certain sequence control operations, just like a coolant on and off, fixture clamping on and off, and the tool changers. Basically, the ATC is supposed to move to certain positions, and then you have to identify the tool and then take out the tool and change the tool. So all these operations are the sequential control operations. So as I was mentioning, the hardware functionality required is different, but the basic hardware that is executing all these functionalities are now combined together. Otherwise, you will see that this is the functionality of a motion controller. This is a functionality of a PLC here. This is the functionality of the motion controller. And the rest of the functionalities are part of a simple CPU actually, simple processors basically. So that way all combined together now. So again, these are the basic computing hardware details. So not going into the details. We all know now by now, because all computer systems should have these basic capabilities. Now, when it comes to the control of a machine tool, axis and the spindle speed. So this is very important to understand. When we have understood the PLC, we'll certainly have another session where we will be discussing about the motion control instructions. We have not yet understood the motion control instructions, because what we have learned is the simple logical control. So whatever lectures I have just taken on the PLC, it is only about the logic control. You might have seen that if this is true, then this is true. If this is to be read as an input value, I have to write something as an output value. But none of these instructions are able to help you in executing any of the motion control. It's only the simple basic logic can be implemented with the PLC functionalities. But in machine tool, we have seen that none of the machine tool comes without any motion. So all the machine tools require the motion to be controlled. And motion control is a very important part of all sort of NC control systems. So what you are supposed to control, you have to control the position and velocity of each axis. So now you will see that there's a motion required to perform in X axis, Y axis, Z axis independently or simultaneously. So you need to have some calculations done on the velocity and the accelerations. So all that we'll see that what all is required when we do the motion control understanding. But then the position and velocity of these linear axis, and then there's a rotational speed of a spindle actually, because you have to maintain the RPM of the spindle. If I am running at the 3000 RPM or 2000 RPM, 1000 RPM, all that has to be controlled so that the speed variation should not be there. There has to be a closed loop control for the rotational axis of a spindle. So that's a continuous speed will be achieved through that. So these kind of motion control are required on most of the machines. Now, when we talk about the CMM, then the probe is not rotating, so that this is not required, but other position and velocity axis control is required for each axis. Same is with the additive manufacturing also. There is again also only the linear motion controls of the multiple axis. There is no rotational speed or rotational motion control of the spindle. Now then we talk about the sequential control and the machine tool functions. So coolant control, tool changer, fixture clamping, load, part loading, unloading, that will be there. And the third one, as I was mentioning, the personal computer, which is having the same capability as we all understand from a normal PC. This I have already explained how the three different programs, that is how we started that, and then we learned about the basic logic control part. But this part we have done, the basic logic control part we have already done. And now we need to understand the CNC part programming, and to some extent the operating system software, basically how it has been done. Only with the combination of these different hardware capabilities and these three different software environments, you will be able to control any of the CNC machine. So these auxiliary functions, I'm sure that now you have learned the basic PLC instructions. If I ask you to write a basic program for the CNC auxiliary functions, you can easily do that. So maybe for a particular instruction. So there are M codes basically. Whenever it comes to the auxiliary functions, you will always find all those M codes will be used actually. So M codes will be deciding whether the spindle on and off, the coolant on and off, and there are additional M codes for the fixture clamping and then the part loading, unloading. So all these functions are being done with the help of M codes, and G codes are the preparatory codes for the controller. So again, that part we will see that. So we can easily write the ladder logic for these basic functionality. When some condition is met, then you can just make the particular digital. So most of these functionalities till you're not talking about the counters. Rest of these are basically the DIs and DOs actually. So you will read some of the inputs and then you will be controlling some of the outputs on the machine, and that DI-DO interactions or the relations can be easily programmed with the help of a ladder logic that you have learned. Now, when it comes to the DNC, that is the distributed numerical control. This is again a very good terminology being used in the industry. So earlier when we are talking about the DNCs, we are talking about the direct numerical control. So terminology started with the direct numerical control, and then it has come to the understanding of a distributed numerical control these days. So what is the difference between direct numerical control and distributed numerical control? You can understand from here. Earlier, when computing systems are very costly and bulky actually, so then you will not be having a computer associated with each machine. So if you can see here, you have a one single mainframe computer, which will be in a file server or a single controller hardware. But then your machines are multiple actually. So you have a multiple machines and each machines can't afford a computer. So what this file server or the single mainframe computer will be doing, it will be just passing one single instruction of the code to each machine. So this has been designed. So there is one computer controlling multiple machines. This is what is known as direct numerical control. It means this controller is directly controlling individual machines. It will be passing the instructions. So once this machine execute one instructions, for example, if I just give n10x15, then it will execute that motion. And then once it is over, it will again ask for the next instruction from the same file server. So that is the way direct numerical control used to work. But nowadays we can easily afford the computers on individual machines. So then it has been changed to distributed numerical control. So numerical control is still there, but now it is not communicating the individual instructions of the program. It can directly download a bulk program into the machine, and the machine computer is responsible for executing that program one by one, step by step. But then there is an advantage of having a distributed numerical control, as we understand the network of the computers will help, or the network of the computers will be doing as same way we would be looking forward for the network of machine tools. So DNC concept, if you see that now we will be having a capability of communication between the machines. Sometimes it is called as M2M communication, also machine to machine communications. So in distributed numerical control, you have a capability to upload and download the programs to another mainframe server or the mainframe computer here. So you can download the NC part program depending on the job. So operator can just select which job to be, or even sometimes the digital instructions or the process sheet is also appearing on the screen of the machine tool. So now he need not to even select the program. He has to just select the job instruction. So if he has to execute the program for a particular part that is being scheduled by the manufacturing scheduling. So you can just look at those instructions, select the program. It will download the program at the same time from the main server. So NC part programs can be downloaded what all tools are required for this job. All these instructions can appear on that machine tool setup instruction can be appear on the screen. So all that can, so these are the part of the process sheet. So machine operator instruction, the tool setup instructions, tool details, part programs, production schedule, actually, that is what I'm just saying. So all these information can be downloaded onto the machine controller or machine computer. Now, there are some information that the individual machine tool will also be uploading back to the main computer. And this is something is the forming the basis of the industry 4.0 implementation, because now you have a two-way exchange of information from the machine tool. So you can capture the piece counts, how many parts are being produced by the CNC machine, that is being communicated back to the main computer. Machine cycle time is being communicated, tool life statistics, machine utilizations, product quality parameters. So then with the help of a distributed numerical control, now your individual machines are having their own computer to execute the basic motion requirement or the basic logic part and the basic program editing functions. Apart from that, they are also responsible for communicating with another server or the bigger mainframe computer through which you will be exchanging the data two-way. So you will be your manufacturing management system will be keeping record of all these uploaded parameters and maybe utilizing it for the analysis. And then machine is also able to download whatever the various instructions required or the part program required. So that way two-way data exchange can happen when we talk about the distributed numerical control these days. So it started with the direct numerical control concept earlier, but now it is being used as a distributed numerical control. So term remains still same, the DNC. It's the same functionality. Fine. So I think this is just a quick introduction about the NC. Now we will be going a little deep into understanding the positioning system. So numerical control positioning system is very important part of all the machine tools. And we need to see, so I will be just taking you through the basic understanding how this positioning system work, what kind of basic computation you're supposed to do. So right now we are just trying to understand those basic computation ourselves, but we are not supposed to do those computations ourselves in the machine actually, because now that is being responsibility of the machine tool computer. So we will do all those programmings to take care of those functionalities. But for this exercise, we will go through the basic understanding. So when we talk about one single axis of the motion, if you see here, so you have one axis like this. So you have a motor coupled with a lead screw over here. We are taking an example of a lead screw because that is common in the machine tool, but sometimes you will be also using a timing belt and the pulley arrangements to make that particular axis of the motion possible. Fine. So in this case, you have basically, once you are getting the information from the part program, now your controller has to execute that motion. As I was keep giving the example that once wherever you have this instruction N10 X15 to be move, and then certainly you might have already given the G01 instructions earlier. So linear interpolation is to be applied from the current position. You have to move to the current next position, that is the X15. So I'm talking about one single axis right now. So how those actual motion being performed by the machine, what kind of input is available to the motor. So controller side, we understand, we have given this instruction. Let's try to go deep into the technology, which will be converting this alphanumeric instructions into the actual motion that is going to happen into the machine tool. So we all understand there is a lead screw for making the work table moving on this particular axis. So there is a work table over here on which you will be placing the work part. So work table is there. You will be placing in a work part on top of that. Then there's a cutting tool which will be now rotating in this case. So you will be performing the relative motion between the cutting tool and your work part. So normally we keep the cutting tool fixed in the this particular x-axis. Only it will be moving up and down in this case. The rest of the XY motion, Z motion, all Z motion is being done by the cutting tool, but XY motions are being performed by the table itself. But for that you need two axes. Right now we are only utilizing one axis. So in this case only the motion will be performed in either of these two directions. So plus X or the minus X in that case. Now if we look at this positioning system, we need to identify the various elements. As I was saying, the motor is being understood. You have a Lead screw, certainly there will be a bearing and coupling over here that is not being shown, but that is being understood now. When we look at the transmission mechanism, we'll understand that part as well. But the basic thing is that we need to generate a relative motion between the cutting tool and the work part, and that is to be generated precisely the motion that is required. So when I say the x15 is means that I need to move this x-axis to 15 millimeter. Now, how this 15 millimeter precise motion is being produced by this axis, that is what we are trying to understand. Now, there are two ways to do that. That is what the terminology you might have learned earlier also, the open loop and the closed loop in this case. You all understand when we talk about the open loop, closed loop, in open loop, we are not verifying whether the position is achieved or not. In the closed loop, we are continuously getting a feedback to check the final position reached or not. So first thing I think is very fairly known to everyone actually. But second point that I have written here is even more important. In what scenarios basically you will be using these type of controls. It's not that certainly we all understand that the closed loop control is always good, but there is always a price to the good actually. So it doesn't require to be implemented everywhere. And a very good example of a open loop control is your 3D printers these days. So 3D printers are mostly coming with an open loop configurations. And that is how most of the printers are being implemented with the stepper motors only, without having the feedback there. But let's try to understand where these scenarios are important. Now, open loop means if I give a command and if there are not much forces basically to resist this motion, and forget about the slip and other thing, but let's assume the scenario when the forces are not very high, and then the open loop can work very well actually, because whatever we will be commanding, the axis will be moving in that case. So this kind of, and you can easily correlate that in 3D printer there are no forces as such, very minimal forces to move the move your base platform or the hot bed basically against the extruder. So there is no force coming on that. That is how it is successful. Why to invest in the closed loop servo systems basically, when you can easily perform those motions with the help of a belt and pulley coupled with the stepper motors. Now, when it comes to the closed loop, it is important when there are large forces and there is a good chance that your axis may not have achieved the same displacement as is required because of these resistive forces. Then in that case, closed loop is very important because I need to make sure that the axis should move in spite of that resistance. So they need to pump in more current into the motor to reach out to the destination which is required in that case. So machine that perform the continuous path, if you see here, and have significant cutting forces, then you will be obviously going for the closed loop systems. This is the important point of consideration, and we can easily find it out which is suitable for the different applications. Certainly this will cost less, that is how it is being preferred, and then closed loop systems comes with its own hardware cost associated with it. So that's how you can make a good trade-off between the functional requirement and the cost of the system. So this is all about the basic NC positioning system. Tomorrow class, we will start understanding the open loop positioning, and then we'll discuss the closed loop positioning, considering a basic motor configuration and the electrical pulses, how that will be counted, and then it will be used for generating those motions. So that is all for today's class. I will be stopping the class here only.